What if I told you the Earth is spinning faster than ever before? In July 2022, scientists recorded the shortest day in history, by a fraction of a millisecond. Our planet, this massive blue marble, is picking up speed, and no one is entirely sure why. In labs and observatories around the world, scientists are racing to solve the mystery. Could it be shifting glaciers, deep forces in the planet's core, or something else entirely? And what does a faster spinning Earth mean for our lives, our technology, and the future of time itself? Stay with us as we uncover the science, the surprises, and the real-world consequences of the day the Earth spun too fast. To understand why the Earth is spinning faster, imagine a figure skater. When she pulls her arms in tight, her spin accelerates dramatically. When she extends them out, she slows down. This principle is called the conservation of angular momentum. Our planet, in a way, is that figure skater. Oceans, an atmosphere, a molten core, massive continents. Any change in how Earth's mass is distributed, from its very center to its surface, can alter the speed of its rotation. It's a delicate cosmic ballet, where every moving part influences the whole performance. And right now, the choreography is changing. One of the leading suspects in this planetary speed-up is something called the Chandler wobble. Picture a spinning top that's just starting to lose its momentum. It doesn't just spin perfectly, it also wobbles slightly. The Earth does the same thing. Its axis of rotation traces a tiny, irregular circle at the poles over a period of about 433 days. This wobble is a natural phenomenon discovered by American astronomer Seth Carlo Chandler in 1891. For years, this wobble has been a consistent feature of our planet's motion. But recently, something strange happened. The wobble has been mysteriously diminishing. Scientists have observed that from about 2017 to 2020, the Chandler wobble became less pronounced, almost disappearing for a while. It's like our planetary spinning top suddenly became more stable. While the exact reasons for this change are still being debated, some scientists theorize that this reduction in wobble could contribute to the overall increase in spin speed. If the planet isn't expending as much energy on wobbling, perhaps that energy is being converted into a faster rotation. The story of our planet's changing spin doesn't just involve celestial mechanics. It's also deeply rooted in Earth's own history, specifically its icy past. For thousands of years, during the last ice age, colossal glaciers, some several kilometers thick, pressed down on the northern parts of our planet. This immense weight literally squashed the Earth's crust. Now that those glaciers have melted, the land is slowly springing back up, a process known as post-glacial rebound or isostatic rebound. Think of it like pressing your thumb into a soft rubber ball, watching it slowly regain its original shape. This process is still happening today, thousands of years after the ice disappeared. This rebound is a prime example of mass redistribution on a planetary scale. Canada is rising. Scandinavia is rising. The Earth's shape is subtly altered, less squashed at the poles, a bit wider at the equator. This change, however small, impacts rotation. Figure skater pulling her arms in. The planet spins faster. This slow, steady process has been accelerating rotation for centuries, a silent force against the moon's braking effect. But there's a modern twist: climate change. Greenland's glaciers melting rapidly, Antarctica's ice melting rapidly. That's another powerful driver. Trillions of tons of ice flow into the oceans. Mass moves from poles toward the equator. That has the opposite effect of rebound. Figure skater extending her arms, which should cause the Earth to slow down. Two competing forces, rebound speeding us up, and rapid melting trying to slow us down. Earth is currently accelerating, which suggests speeding up effects like rebound and perhaps changes in the core are overpowering modern ice melt slowing. Complex, dynamic balance of planetary forces. The Earth is fluid and responsive, not a simple solid sphere. Melting glaciers, earthquakes shifting plates, ocean currents, all contribute to the dance of rotation. Understanding this spin is understanding the pulse of our living planet. So, the Earth is spinning faster. What does this mean for you and me? Will we start losing sleep? Will our morning alarms feel like they're going off sooner? The short answer is no, not directly. The change is so minuscule, a few milliseconds. Our biological clocks, which are far from being precision instruments, won't notice a thing. you won't feel rushed. The sun will still rise and set in what feels like a normal 24-hour cycle. The rhythm of our daily lives remains fundamentally unchanged, governed by light and by dark. Our bodies are simply not sensitive enough to register such a subtle shift. They provide the unwavering beat for our global tech infrastructure. The problem arises because UTC is designed to stay in sync with the Earth's rotation. We want official time to match the position of the sun. Earth's spin is irregular, sometimes speeding up, sometimes slowing down, so atomic time and planetary time drift apart. To correct for this, international timekeepers have added a leap second when they drift by almost a full second. Historically, these were positive leap seconds, adding a tick so the wobbly Earth catches up. We last added one on New Year's Eve 2016. But what happens when the Earth starts running fast? For the first time, we may need a negative leap second. That means subtracting a second from official time to let atomic clocks in the planet realign. It's simple in concept but terrifying for engineers. Many computer systems handle an added second. 23, 59, 58. 0000. Skipping 23.59, 59. But a vanished second could trigger unpredictable crashes and data corruption across the globe. The concept of a leap second seems trivial, a tiny blip in the grand scheme of things. But in our interconnected world, that single second is a very big deal. Think about the global financial markets, where billions of dollars are traded in high-frequency transactions time-stamped to the microsecond. A missing second could throw algorithms into chaos, corrupting transaction logs and creating a nightmare for auditors. Or consider the global positioning system, which relies on the precise timing of signals from satellites to pinpoint your location. Car navigation, airplane guidance systems, ship navigation. The internet itself is a symphony of synchronized servers. When your computer connects to a website, it performs a handshake with a server that is timed with incredible precision. A negative leap second could disrupt these protocols, causing connection failures and data synchronization errors across vast networks. Major tech companies have already voiced serious concerns, pointing out that even positive leap seconds have caused problems in the past. Because of these potential problems, the international community of metrologists has made a momentous decision. At the General Conference on Weights and Measures in 2022, they voted to abolish the leap second altogether by 2035. Instead of trying to keep our atomic clocks perfectly tethered to the Earth's wobbly rotation, we will let them run free. This means that, over time, our official clock time, UTC, will slowly drift away from solar time, the time based on the Earth's spin. The sun might be at its highest point in the sky a few seconds, and eventually minutes, after our clocks strike noon. This decision marks a fundamental shift in how we define time. We are choosing the clock of the atom over the clock of the Earth. What if this trend of acceleration continues? What does a faster spinning Earth look like in the distant future? Scientists are exploring several fascinating, though highly speculative, possibilities. If the current acceleration is just a short-term blip, then we may soon see a return to the long-term trend of slowing down, dominated by the moon's gravitational pull. However, if the forces causing the acceleration, post-glacial rebound, potential changes in the core mantle dynamics, prove to be more dominant and persistent, we could be entering a new epoch of planetary motion. A consistently faster spin over geological timescales would have profound effects. The most fundamental change would be a shorter day. This wouldn't happen overnight, but over millions of years, the 24-hour cycle we take for granted could shrink. This would have massive implications for the evolution of life. Biological rhythms, or circadian clocks, are deeply tuned to the length of the day. A more dramatic and long-term consequence would be a change in the planet's very shape. The centrifugal force at the equator would increase, causing the Earth to bulge out more around its middle. This could alter sea levels, with water tending to pool more at the equator. It might also affect tectonic activity. It might also affect weather patterns. The Coriolis effect, which influences the direction of winds and ocean currents. A faster spin would mean more powerful and tightly coiled storms, changing the face of our global climate system. It's crucial to remember that these are extreme, long-term scenarios. The changes we're observing now are measured in milliseconds per century. We are not on the verge of a planetary catastrophe where we'll be flung off the surface. but studying these trends gives us an incredible insight into the powerful and subtle forces that govern our world. It reminds us that we live on a dynamic planet, not a static stage. The Earth has changed its speed before, and it will change it again. The scientific challenge, and the adventure, is to understand why. When we look up at the cosmos, we see a universe in constant motion. Galaxies collide, stars are born and die, planets spin on their axes. Our own planet is part of this grand, dynamic celestial dance. The fact that its spin is changing is not a sign of malfunction. It is a sign of life. It's a message from the deep interior of our world, from the shifting continents, from melting ice caps, all communicating through the language of physics.